Hello, Precalc C. Welcome, welcome. Snow day, Friday, whatever this is, January 19th. We're gonna make a video, um, and I'll explain who this is for later, but this is basically for period 6 and period 9. We did this yesterday in class. So that's what's going on. We gotta learn our last thing. Our last thing is about conic sections in polar coordinates. So let's go. I don't have any of the correct equipment to be doing this. So I am using Zoom, which is just a terrible way. So the resolution is going to be bad, the tech is bad, everything's bad. But um, I don't care, and so neither do you. Um, let's begin. Sure. Let's begin. Um, Here is what I want you to do. I want you to get out the packet called um, conic sections in polar coordinates. So conic sections in polar coordinates. And what I already told, um, period 9 yesterday, and so this should be mentioned is, this would be a good moment just before doing this. Okay, this seems weird, polar coordinates. You're probably thinking, when we haven't done polar coordinates in 6 or 7, 8 months, something like that, since like March or April of pre-calc B. That's true. So you may have forgotten things, and let's do a quick recap, therefore, of polar coordinates, and then let's talk about why they might be useful. And they're going to come up again next year too, so they're not gone. What are polar coordinates? Well, they're an alternative way of um, doing coordinate geometry. So in normal coordinate geometry that you learn in middle school or whatever, you have some sort of point x comma y, and that point x comma y tells you how far you go over, in the along the x-axis, and how far you go up along the y-axis. Okay, so that's like fine, but in the polar coordinate system, instead, we have a thing called a pole, and that is kind of playing the role of the origin. And then we have this thing, which is called the polar axis. Polar axis. And now points in the plane are measured not by where they are relative to a pair of perpendicular axes, but instead by how far they are from the pole and how far they are from the polar axis. And so if we take a point in the plane and we give it polar coordinates r comma theta, the meaning of that is that the point is r away from the pole, and the counterclockwise angle of rotation to that point is theta from the polar axis. Okay, so cool. And now um, yeah. What else is there to say? Then there are some sort of subtleties, such as this is, if theta is positive, it means that we rotate in a counterclockwise fashion. Theta is negative, then it means we go back the other way, rotating clockwise. If r is positive, then we go sort of like, forward. If r is negative, we go backwards. Okay, so I'll assume you got that under control. Great. What else is there to say about this? Well, um, we may also, sometimes this is convenient, we may simultaneously pursue analyzing some figure with polar coordinates and also with rectangular coordinates. This is kind of like a common thing to do. So some people kind of brush over this, and maybe it's a little bit confusing. But if you have a plane and you establish a polar coordinate system, and then you also establish a rectangular coordinate system sort of on top of it, and you do it in a particular way, which I would call the obvious way, which is that you let the positive x-axis be on the polar axis, and you put the origin at the pole. So then this becomes, the y-axis. Then it's possible to take a point and simultaneously give it a pair of uh, rectangular coordinates. And so I'm describing the same point in two different ways. One in blue with the polar coordinate system, and one in purple with the rectangular coordinate system. And of course, that means that this segment over here is x, and this segment over here is y. Okay, and so if you are doing this, analyzing a figure in both coordinate systems at the same time, then you end up with some general relationships between x, y, r, and theta. And okay, what is one of them? We did this in period 9. Uh, that x squared plus y squared equals r squared is one fact relating x, y, and r. That is relating the x coordinate, the y coordinate, and the r coordinate of a point labeled two different ways in the two different systems. It's also true that that sine theta is y over r, and therefore some people just say that y is r sine theta. And then it's also true that cosine theta is x over r, so that x is r cosine theta. And then it's also true that the tan of theta is y over x. Okay, and so these are sometimes called conversion formulas or something like that. They're conversion formulas because they enable one to convert a to convert a uh, uh, an equation that's in polar coordinates to an equation in rectangular coordinates because of this. Okay, good. What was the other sort of prep thing to say, which is that why would we sort of want to do conics in polar? And there's sort of a reason for this, and the reason is the conics are really important, man. One reason why, well, probably you're already convinced that parabolas are important because quadratic equations are important. Why are quadratic equations important? Because lots of things in our world are quadratic. In particular, gravity. So there's this gravity thing that's happening on Earth, and because gravity is an inverse square law. Do I know this? Yeah, sure I do. The force due to gravity is going to be like, some constant. What's the symbol for that? Symbol for that is like, proportional to the product of the masses of the two objects and the radius squared. So because gravity is an inverse square force, then things, kind of fall quadratically. I think that's actually not even. Let me just erase the last like 3 minutes of everything I just said. There are reasons why conic sections are really important, and one of them is that they do describe the kind of macroscopic behavior of objects kind of in our solar system. So if there is the sun, for example, dun, 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 then objects, you might know, move around the sun. And so things move around the sun in an ellipse. And they move around the sun with the sun at one focus and, something else at the other focus. Or maybe it's just better to say that every orbit of the planets and comets and other things that are gravitationally attracted to the sun are going to be moving around the sun um, with the sun at one focus. And so if you give me some planet or whatever, and then one thing that I might really, really care about is how far that planet is from the sun, and also sort of the angle that that planet is making from the sun. So these are very sort of kind of classical things to kind of care about. If you are studying orbits, then you would definitely want to establish a polar coordinate system for your conic sections, because the sort of relevant fact is, how far is the planet, from the gravitationally attractive body, which is that one focus. Okay, and in some sort of more advanced class, with a little bit of calculus, you can actually prove this fact that Kepler discovered, 400 years ago, which is that planets move around the sun in the shape of an ellipse. Okay, with the sun at one focus. All right, with that kind of extremely crappy intro, let's get to the real thing. The real thing is this packet called Conic Sections in Polar Coordinates, which I passed out on um, Thursday. Let's do it. So ready? Here is the idea. The idea is we have a focus, so boom, focused, and we have a directrix, and the directrix is over here. Chop chop, directrix, and the goal is to represent the conic sections in terms of this focus and directrix. All right. Well, we already know based on last week that the new definition of the conic sections enables us to simultaneously analyze the parabola, hyperbola, and ellipse all at once because they're really just the same object, and what matters is the eccentricity. And so I'm now going to draw a kind of generic conic section. Is it a parabola? Is it an ellipse? Is it a hyperbola? It doesn't matter. It's all three at the same time. And what we are going to do now is establish a polar coordinate system. And the polar coordinate system that we're going to establish is, just like I've been indicating, with the pole here at the focus and with the polar axis, in this first case at least, with the polar axis perpendicular to the directrix. Okay, having established this polar coordinate system, now I have one goal. My goal is find the equation of this. Oh, one more thing to mention is that there is this letter P, which I am going to consistently use for the distance between the focus and the directrix. Okay, so backing up a little bit, I have a focus, I have a directrix. If you give me a particular eccentricity, then we know that that generates a conic section. There's my conic. Now I establish a polar coordinate system. How do I establish the polar coordinate system? In this case, I establish it with the focus at the pole, the polar axis. I can even write polar axis with the polar axis perpendicular to the directrix, and with the directrix, sort of to the left of the polar axis, so to speak, and with the focus p units away. So in other words, I established the scale of my system so that these are p apart from each other. Okay. And now what are we going to do? We're going to do the obvious thing, which is to pick an arbitrary point on this conic section and find the equation of this object. Okay, well, this is r comma theta. Of course, we're going to do this in polar coordinates because I want the polar equation. And all right, once I decide to call that point r comma theta, now I'm going to apply the definition of the conic. And sort of by definition, there's only one thing I know about this conic, which is that the distance to focus, distance to focus over distance to directrix is E, the eccentricity. Okay, so for this arbitrarily chosen point, r comma theta, what is the distance to the focus? Well, the nice thing, and I've kind of been mumbling and rambling about this for the past 10 minutes, but the nice thing about doing this all in polar coordinates is that in polar coordinates, if you place the focus at the pole, then the distance to the focus is automatically just r. And okay, now the next question is, what is this distance here? How far is this arbitrarily chosen point from the directrix? Well, now I have to do a little bit of geometry. I should probably work in the other sort of fact about this conic, which is that this is theta, which means that this is the counterclockwise angle of rotation. Here's theta. Okay, great. So now what? Now we will do some geometry to figure out what that is. And here I think the geometry is kind of obvious. There's multiple ways to do this, but probably the simplest thing to do is to drop a perpendicular here. If you drop a perpendicular here, then since this is a right triangle with hypotenuse r, and this is theta, then that makes this r cosine theta. And that's relevant because, therefore, this, you could also have dropped the perpendicular this way. This, if this is, one second. If this is r cosine theta, well, this is p, and therefore I've determined that the distance from this arbitrarily chosen point to the directrix is p plus r cosine theta. Okay, we're going really slow, so let's pick it up a little bit. Therefore, what I conclude from this picture, applying the definition of the conics, blah, 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 is that this r over p plus r cosine theta equals e the eccentricity. And okay, great. What is going on? My children are awake now. 1 second. All right. Let's go. You could stop there. However, it is usually what you want to do is to write your polar equation in the form r equals, because we want to think of it as kind of like a function which takes theta as input and outputs an r value. And so we're going to do a little bit of algebra 1 to this equation now. You get r equals e times p plus r cosine theta. And then we get r equals ep plus er cosine theta. Okay, now we subtract and we get r minus er cosine theta equals ep. And if you factor 1 minus e cosine theta equals ep, I don't know if you guys can hear that. Kid noise is downstairs, but okay. ep over 1 minus e cosine theta. All right, so there was nothing challenging about that. That was just essentially just solve for r is what we did. Just because that's just what we always do when we come up with an equation in polar coordinates is we write it in the form r equals. And now you can think of this as an equation. It's an equation which takes as an input theta and outputs an r value. And so, this will therefore determine the curve, the conic section. Okay, and I think it's important to clarify that, so this is kind of the equation, but this is the correct equation according to, oh my God, I have to run downstairs and tell my son to shut up. This is the equation assuming from multiple assumptions. This is the correct equation if, 1, you have to put the focus at the pole. 2, this is the correct, another thing that was sort of built into this diagram is that the directrix was to the left of the pole. Another thing that was built into this derivation is that the eccentricity was E. Eccentricity E. And another thing built into this equation is that the distance, the distance between, oh my gosh, the distance between the focus and directrix is E, the eccentricity. Okay, in other words, if you accept these four, if you build these 4 things into your problem, that you have a polar coordinate system with the focus at the pole, eccentricity E, the directrix is to the left, and specifically, sorry, that should say P, and specifically P, if it's P units to the left, then this, with these 4 assumptions, then this is the correct equation of that conic section, of course, in terms of E and P. Okay, that was kind of a horrible explanation. Let's just keep going. 1 down, 3 to go. On the very same packet, you have another picture, and now we're going to just go a lot faster because this is going to be kind of repetitive. Here we have another point. We call this the this is the focus. Sorry, focus. And this is the directrix, but now my directrix is like to the right of the pole, And when we establish the coordinate system, the polar coordinate system, I intend to again put my pole at the focus. And again, I am going to make my polar axis to the left. Can I do this? Yeah, let's do that. Again, I'm going to make my polar axis to the, not to the left. Again, I'm going to make my polar axis perpendicular to my directrix. But this time, the polar axis is going to intersect the directrix, whereas that was probably the most precise way of explaining what happened over here, is that this time the polar axis was sort of going away from the directrix and not intersecting the directrix. Uh, the normal human thing to say is just the directrix is to the left of the pole, but more precisely, if you establish your polar axis so that it's perpendicular from the directrix, but that ray is not intersecting the directrix, you get this figure. But the other figure that you could get is this one, where you again establish the polar coordinate system with the focus at the pole, and again the polar axis is perpendicular to the directrix, but now it's kind of intersecting it. And so, okay, if you do this again, we will use the letter little p to refer to the focus directrix distance. And now we can sort of describe our conic. Well, what does our conic look like? Well, it depends what kind of conic it is. Could be a parabola, could be an ellipse, could be a hyperbola, whatever. Okay, and something that sort of happens. So, okay, so now we're going to do the exact same thing, which is to pick an arbitrarily chosen point on this object and kind of get to it. All right, and so one thing that I know to do with sort of experience is to always pick a point in the first quadrant. So here is my arbitrarily chosen point. This arbitrarily chosen point is r comma theta. And again, what does that mean? It means that the distance to the focus is r, and it means that this is theta. And again, I'm going to apply the definition of conic, and the definition of conic is that distance to focus over distance to directrix equals E the eccentricity. Okay, great. And again, it's very convenient in polar coordinates that this point is our way. Oh my God. And now I need to figure out what this is, this distance to the directrix. Okay, well, the simplest thing to do is drop this perpendicular down and to observe that this leg of this right triangle is r cosine theta. And if this is r cosine theta and this whole thing is p, then this is p minus r cosine theta. Okay, so everything I'm doing is correct, and so that's nice. The distance to the focus is r, and the distance to the directrix is p minus r cosine theta. Okay, there is a potential sort of pitfall, however. Let's see, let me pick some new sort of color like orange or something. There is a way in which this whole thing could go wrong. And, I keep saying choose an arbitrary point. And so if you are truly allowed to choose, an arbitrary point, then you might be thinking, well, what if I pick a point over here or something like that? And in fact, based on the white space of the packet, half the people or more, do pick that point for their arbitrarily chosen point. And it seems like there will be no problem, because how could that possibly, affect the things if you put your point in a different place? Well, if you put your point in a different place, things get kind of complicated. And so basically, my advice to you is to not do this. Specifically, when your angle is obtuse, there is a high potential for confusion. Notice that I have, in the first case, when I did it carefully in purple, I picked a theta that was in the first quadrant. But in this second time, when I'm explaining this potential pitfall, I put the angle in quadrant 2. And if you put the angle in quadrant 2, you could easily screw up. And that's because in quadrant 2, cosine is negative. And so when you try to come up with the equation, you could easily make a mistake. For example, you might not know what to do with this is sort of theta, and then so sort of what is what is the length of this segment? Maybe we just shouldn't even bother talking about this sort of what not to do kind of thing. But I'm recommending strongly that you always, when given a chance to pick an arbitrary point on your conic, that you always pick it in such a way that the arbitrary point is in quadrant one. And if you always put it in quadrant one, then sine and cosine will always be positive there, and that's just going to go a lot better. Okay, back to this derivation. What do we get? We get r equals EP minus ER cosine theta. Again, I'm just multiplying through by that denominator to get rid of all the fractions. Now I will solve for r. So I just move this over to the other side, factor out an r, and divide. Okay, and now I once again have this beautiful equation, EP over 1 plus E cosine theta, and this is the correct equation given a bunch of assumptions. What are the assumptions now? Well, again, one assumption is that this formula is correct, assuming you have put the focus at the pole. The other assumption that we have made built into this problem is that the directrix is to the right. Directrix to the right of the pole. There are more precise ways of saying that, but that's pretty good. Another assumption built into this problem is that the eccentricity is E. And another assumption built into this problem, of course, is that the distance between the focus and the directrix is P. In other words, if your directrix is P units away from the focus, if your focus is at the pole, if the directrix is to the right of the focus, all the things that were sort of built into this to this picture, then this is the correct formula for your conic section. And of course, this is for a generic eccentricity. If you give me a specific eccentricity, then whatever. Okay, so in class we would just sort of do all these. By the time like we've done one or two, the rest are almost a waste of time. So I don't know. Should we do one more? Some years I just stop here and let you finish the other two, or I just kind of like do it on the board with us. Let's do one more. If you turn to page 2 of this packet, then you just get a sort of very kind of repetitive. And once again, I personally believe that even though there's some redundancy here, it's good practice, and also it's simpler to just have 4 separate formulas, to just do 4 separate derivations. So what's the other possibility? Well, the other possibility is that the directrix is below the focus, so to speak. And if we're being more precise about this, we are still going to put the pole of our polar coordinate system at the focus. We are still going to have a polar axis like that, but now the directrix is parallel to the polar axis. That's really what's going on. Okay, and so how does this affect things? Well, you're still gonna have some kind of conic, and you just kind of repeat the whole process over again, which is to find the equation of this conic. How do we find the equation of this conic? Well, we are doing it in polar coordinates, and so we pick an arbitrary point on the arbitrary conic with coordinates r comma theta, polar coordinates, and now we just find the equation in polar coordinates of this conic section in terms of the eccentricity. And one more time, we continue to consistently use the letter little p to represent the distance from the focus to the directrix. Okay, so now maybe I'll just go like as fast as I can without further comment, because I think we know how to do this. Definition of the conic says distance to focus over distance to directrix is E, the eccentricity. The distance to the focus is r, and the distance to the directrix is easily determinable because since this is theta, that's what theta means, then this is r sine theta. And there it is. Distance to focus, r, over distance to directrix, p plus r sine theta. um, equals E, the eccentricity. And I can multiply both sides by P plus R sine theta. Subtract. Factor. Divide. And there is my equation. Once again, this time I'll just say it out loud, or I guess I can write it down. What is this equation? This is the correct equation on the assumption that focus is at the pole, focus at pole. Now built into this picture is that the directrix is below the pole, specifically that the distance between the focus and the directrix is P, and then also that the eccentricity is E. Okay, so if you give me a conic with eccentricity E, if you put the focus at the pole, if the distance between the focus and the directrix is P, and the directrix is below the pole, then you get this equation. Okay, so what do we have? We have basically four equations in polar coordinates. They all have an E and a P parameter in them. E is just the eccentricity. P is just the focus directrix distance. And the four equations are all just the four possible orientations of the directrix with respect to the pole and the polar axis. Okay, so what do you do with these four equations? You kind of just memorize them, or frankly, this entire derivation, once you've done it, say twice, takes about 1 minute to redo this entire thing. And so if you forget ever, then you can just rederive it. Now, I mean, there's a couple of basic things to kind of realize, which is that the cosine ones are all going to involve the directrix being vertical, being perpendicular to the polar axis, and the sine ones are all going to have to do with the directrix being parallel to the polar axis. So really, anyway, you can figure it out. All right, good. All of that was just like the warm up to like the real thing. This is gonna take about 20 minutes now. Let's go. Yikes. Um, turn to page 3. We are now going to do a single problem, and we're going to do this single problem in 4 different ways. Okay, let us begin. This is I call this I think this is pretty challenging, or at least some of the ways are challenging, but by the time we're done, we will have learned everything. Okay, and so here we go. I'm giving you an equation. R equals 12 over 3 minus 5 cosine theta. Goal, figure out everything. Graph it accurately, figure out what kind of conic it is, find, A, B, C, D, E, P, everything. Have an equation of this, maybe in rectangular coordinates, blah, blah, blah. Okay, what can we even get out of this? Well, this looks suspiciously like the formula that we already know. The formula that we already know is R equals EP over 1 minus E cosine theta. Okay, do we know that? Yeah, we just kind of do. I mean, if you want me to throw it back up on the screen, I will. But this was the formula in this particular situation when the directrix is to the left of the pole, blah, blah, blah. Okay, so all of these formulas have in common that the numerator is EP, and then this is always like a 1. Okay, so this is not like anything deep I'm saying right now. The smartest thing to do first here in this problem is to make this a 1. So just like make that a 1. How? By just doing it, man. So if I divide the top and bottom of this equation by 3, then I get 4 over 1 minus 5/3 cosine theta. Okay, great. So that's making me very happy now because I now have an equation, in standard form, so to speak. Um, Man, bad at this software. I now have an equation in kind of standard form. And based on my previous knowledge, then I can tell you that the x yeah, I yeah, I can tell you that the eccentricity is 5/3, and therefore that it is going to be a hyperbola. And also, I can tell you that EP is going to be 4. Again, because we just derived these equations, sort of in general earlier. Okay, well, if EP is 4, then, and E is 5/3, then, 5/3 P is 4. And so I can pretty easily calculate what P is. P is going to be 12/5. Okay, so from a just completely mindless sort of formula facts extraction, here's what I know about this conic so far. I know. Here I shall establish my polar coordinate system. Here's my focus. Here's my pole. Here's my polar axis. Polar axis. Great. And what else do I know? I know that the directrix is going to be to the left of the pole. And I also know that it's going to be 12/5 to the left. Okay, so let's go 1, 2, 3, 4, 5, 6, something like that. And sure, that's probably decent. And now where is my focus? Focus is at the pole. Where is my directrix? Directrix is 12/5 away. So that's like 2.4. So I have now my directrix kind of drawn in. So like directrix. And the equation of this directrix, sort of in rectangular, is like x equals negative 12/5. It's just the vertical line, which is 12/5 to the left of the pole. I know that based on everything that we've done earlier. Okay, and now what kind of conic is it? It's a hyperbola, and it's a hyperbola which is always going to be, remember, the hyperbola is always going to be a little farther from the focus than it is from the directrix. So I'm just kind of, eyeballing it. Going to be something like that. It's going to be one branch, and then the other branch is going to be, sort of over here somewhere. Recall that a single focus and a single directrix will generate this entire hyperbola. The directrix is not going to be halfway between the branches. One branch will be farther out. All right. So I now have a rough picture that's already pretty good. But now I want, kind of like everything else. How are we going to do this? Well, the very first way we're going to do this is the hardest way of all. And the first way, which I call method number 1, is to just figure out every possible deep relationship between D, P, C, A, E, and B. Yikes. Okay. What am I even talking about? Well, let's begin. What's one thing I know? What's one thing I don't know? If you are trying to figure out the parameters kind of this hyperbola, you're probably thinking like, all right, I want to know what A and C are. I want to know, how far away is the focus from the center and how far away is the vertex from the center. The biggest problem that I have is I don't know where the center is. So this right here is the focus, but where's the center? I just don't know where the center is, which is kind of like a drag. Okay, so I'm gonna just drop the center here at some sort of random point, which feels like roughly correct based on my picture. And now I'm gonna try to determine where that center is. Maybe I even write center question mark or something like that. All right, well, what can I say? This is going to be my vertex. This is going to be my focus. So this distance, or maybe okay, maybe that's not what I'm talking about. The simplest thing of all is that this distance from my center to my directrix is D, and the distance from my directrix to my focus is P. Okay, and so I'm gonna figure out what the center is kind of indirectly. Oh my God. And then, of course, this whole thing is C. All right. And so method number one begins with the observation that D plus P equals C in a hyperbola. We did this in class, but anyway, even if we hadn't, I just did it there right now. All right. Is this helpful in some kind of way? Well, it's a little bit helpful because um, I know what P is. P is just 12/5. So really, I know that D I know that D something bad is happening here. Okay. Kind of weird. D disappearing on me. Let me just go back a little bit. What the heck is happening? I'm on some disappearing ink thing. That is extremely disturbing. Let's just close this for a second. Open it back up again. They're all back. Okay, so that's just bizarre, and we have no explanation for why this happened. All right. Good. I love technology. Okay, so back over here, what did I just say? That D plus P equals C. But specifically, D plus 12/5 equals C. This is my P, and this is my C. Okay. Um, and yeah, already you might be sort of thinking something now, which is, okay, I don't know what D is, and I don't know what C is, and I don't know what A is, but I do know what the eccentricity is. So I know the eccentricity. So if I know the eccentricity, then perhaps we can rewrite C and D using the eccentricity. And we can. So we're bringing sort of all the math that we know into this situation. One thing we know is that the eccentricity is C over A. Another thing that we know, we derived this multiple times for the conics, is that the eccentricity is also A over D. And it was these facts which together got us to the fact that like C over A equals A over D, which meant that like D was A squared over C, etc. So hopefully you remember this because that's kind of important. All right, well, keeping all that kind of in the background, maybe I'm gonna do this one more time. Then what I'm now going to do is rewrite C and D in terms of A. So what's D? D is just A over E. And C is just EA. Okay, this is a very smooth method because I know what E is. E is just 5/3. And so if I divide by 5/3, that's like multiplying by 3/5. So here I get 3/5 A plus 12/5. And here I get 5/3 A. Okay, so here I'm going to put a box around this and declare myself very, very smart because what we did, we were sort of stuck. We didn't know what A was. We didn't know what C was. We didn't know what B was, but we did know the eccentricity. And we took this sort of simple, basic fact about hyperbolas that D plus P equals C. We already knew P. We had a number for that. And we re-expressed D and C in terms of A and the eccentricity because we also know the eccentricity, and now I just have a linear equation in terms of A. Okay, so now I'm just going to solve this. I get that 12/5 is 5/3 minus 3/5 times A. And what is 5/3 minus 3/5? It's 25 minus 9 over 15. What just happened? 25 minus 9. Yeah. So that's 16/15. So I get 12/5 equals 16/15 A, and then like some math happens. Did I even do this right? Yeah, sure I did. So then that cancels and we get a 3. And this cancels and we get a 3 and a 4. Taking a 4, dividing both sides by 4, multiplying both sides by 5. And so then if I then yeah. Oh my gosh. So 3 equals 4/3 A. And so A is in fact 9/4. Okay, that was a lot of work to figure out that A is 9/4. And if A is 9/4, that was the secret trick, which now unlocks, sort of everything else I could possibly want to know. Because if A is 9/4, then I can figure out what C is, because C is just EA. And so C will therefore be the eccentricity 5/3 times 9/4. So that's just going to be 15/4. Okay, and once I know that C is 15/4, then I can erase this question mark. Now I have really determined where the center is. And the answer is it's 3 3/4 away from the hole. And it turns out we have that, just by eyeballing it almost exactly right. Um, it's right there. It's right there. And the answer is it has rectangular coordinates -15/4, comma 0. That's what C is, because C is 15/4. And all right, what else? We can also figure out what B is. What's B? Well, I know that in a hyperbola, a squared plus b squared equals c squared. And yeah, so what we have here is like 9/4 squared plus b squared equals 15/4 squared. The smoothest way to do this is like in your head, this kind of like a math team kind of trick, because we see that there are fourths here. So instead of solving this equation, I'll just solve the equation, I'll just ignore the fours and just go like, basically, what do I need? I have a one leg that's 9 and one leg that's like something, and this one is 15. And then when I get whatever what x is, I'll just scale it by 4. But of course, this is just a famous triangle. This is just a 3, 4, 5 triangle dilated by a factor of 3. So here x has to be 12. I'm just avoiding doing the arithmetic here. And if that's true, then and I also dilate by 4, then that tells me that B is 3. Okay, hopefully you followed all that, or you can do your own arithmetic. All right, after so much effort, filling up an entire screen full of scribbles and weird equations, bringing up every single sort of little thing that we know, here's where we are right now. I know what A, B, and C are. And what would we say? A was 9/4, so that's looking roughly correct. Um, and we're good. Can I write the equation of this thing? Yes, I can. This is going to be a horizontal hyperbola, x minus 15, no, plus 15/4, because we're moving 15/4 to the left, minus y squared, and the x coordinate has been stretched by a factor of 9/4. So this is over 9/4 squared, and the y coordinate has been stretched by a factor of 3. All right, believe it or not, this ugly equation right here is the rectangular equation of this hyperbola. So we succeeded. We found the out where the center is. We figured out what A is. We figured out what C is. We have an equation. We know every single possible thing. Okay, this is method number 1. This is the least efficient method, but it's also a good method because we did a lot of learning. Are there some other methods available? Yes. We're going to do the same problem now in 3 different ways, but very quickly. Oh my God. Kids are just screaming downstairs. It's terrible. Okay. So let's go. Here is the focus. Here is the, or rather, here's the pole. Here is the polar axis. And what do we know again? We know that based on the equation that P is 12/5. And so that's why I'm gonna do this. And I'm sort of redrawing the whole picture because that seems like the thing to do. So this was my focus, and this is my directrix. over here, and we know it's 12/5 away. So P, yeah, x equals negative 12/5 is the equation. And I can't remember the color scheme. I guess it's not important. But the hyperbola itself, what does it look like? Well, it's going to look like however it looks. All right, so what is method number two? Method number two, maybe I'll just rewrite the equation just so we have it here. R equals 12 over 3 minus 5 cosine theta. But of course, the first thing we do is to divide by 3. So this is really 4 over 1 minus 5/3 cosine theta. And it is from this that we extract the fact that the eccentricity is 5/3 and P is 12/5. Okay, so having done all that already, kind of like in the past, now this is now method number two that I'm about to present to you, and I'm claiming that it's like better. How does method number two work? Method number two says, yo, when you go to draw the hyperbola, don't just draw some sort of sloppy picture or whatever. Let's figure out exactly where this hyperbola crosses through this line connecting the focus and the directrix. In other words, and this is something that we did on the very first day when we did the point plotting activity. In other words, this point here, this point on the hyperbola that is kind of closest to the directrix, this point must satisfy a very specific equation. That is, it has to also, well, it also has to satisfy the definition of the hyperbola. In other words, the eccentricity has to be 5/3. And if the eccentricity has to be 5/3 for sort of that point, then this point must be in a kind of this point right here must be in the ratio 5:3. So the distance to the focus and the distance to the directrix has to be in the ratio 5:3. And so since I know that the focus and directrix are 12/5 apart from each other, then I can calculate in advance the unique point on a line segment of length 12/5, which divides that segment up into the ratio 3:5. And therefore, I can tell you precisely where that vertex is. Okay. Well, let's do that then. So just basically just solve this equation. Well, to solve this equation, I just say, all right, 8x is 12/5. Divide both sides by 4. So 2x is 3/5, and x is therefore 3/10. So I'm solving this little algebra 1 equation. All right, well, if x is 3/10, then that means that 5x is multiply both sides by 5 is 3/2. And so now we sort of like win. This is making me very excited. It means that this distance right here, this distance is, or this distance, maybe I'll write it, is 3/2. All right, how is that useful? Well, I still don't know where the center is, but I have calculated something. And the thing that I have calculated is, let's think for a moment. If this right here is the vertex, and so this is A, and this whole thing is C. Therefore, this distance that I have just calculated, the distance from the vertex to the pole, I will naturally express as C minus A. All right, this seems like a whole lot of work, but actually, once you've done this once, this just takes like 2 minutes to quickly place that vertex in the correct spot, and then to realize that I now have everything I need. And I know that C minus A is 3/2. Is that enough to calculate C and A? It is, because the eccentricity is C over A, and so C over A is 5/3. And now I just have a little system of two equations in two variables, and I can just solve this system relatively easily. For example, I know that C is 5/3 A, So I just get 5/3 A minus A is 3/2. And so I don't even need this. I think everyone sees how I did that. Um, sure. Right. So I'll just write this right. C is 5/3 A. Um, so take that, stick it in here. And now what is this? So 2/3 A equals 3/2. Okay, this is a little bit anticlimactic because we've solved this problem already. But then if you multiply both sides by 3/2, you indeed get that A is 9/4. So, all right, this was not, this was some amount of work, but it was much, much easier, I think, than what we did in method one. And of course, that once you find that A is 9/4, then you just go on to find that C is 15/4. And once you know that C is 15/4 and A is 9/4, well, then you know where the center is, and then you just have the equation just like we did before. And you can find B and everything. Okay, that was method two. Still a lot of thinking and geometry going on or whatever. Okay, let's kind of wrap this up. Method number three is the I don't want to say the easiest because it actually is a bunch of work, but it is the most mindless. It's pure algebra, no thinking. Method number three says, hey, don't we have some whole don't we have some algorithm to convert a polar equation into a rectangular equation? Answer, yes, we do. We can simply use our algebra skills and just crank this out. No picture, no geometry, no thinking. You just give me the polar equation, and now I'm just going to convert it to rectangular. How? Well, I'm going to multiply both sides by 3 minus 5 cosine theta and get rid of fractions. That seems like a good thing to do. And then I'm going to multiply through. So I get 3r minus 5r cosine theta equals 12. And what's supposed to happen if you are experienced is an alarm bell goes off as soon as you see r cosine theta. Because, as you will recall from last year and also from the beginning of this video, there are these conversion formulas which enable you to convert a polar formula to a rectangular formula or vice versa. And so, what is r cosine theta? Answer, it's just x. So I get 3r minus 5x equals 12. And now I need to solve for r. So 3r equals 5x plus 12. And in order to get rid of the r, I need to square. So if you square both sides, you get 9r squared equals 25. Well, I'll just say, for the moment, I'll just say 5x plus 12 squared. And why did I square both sides? Well, because I've done problems like this before, and I just know that that's the way to go. Specifically, r squared is just x squared plus y squared, see previous diagram. And already I am feeling really good because I have successfully converted this formula from polar coordinates to rectangular coordinates. Okay, now we just finish it off. 9x squared plus 9y squared equals, and now this just kind of gets ugly. 120x plus 144. And now I just have to do a bunch more work that I don't particularly feel like doing, but I guess I'm just gonna do it. Just make sure this is not wrong. Well, I guess I can just look at my own paper. I'm horrified by how difficult this looks like it's going to be, but um, whatever. Let's not worry about it. All right, so let's move all the x's and y's over to one side and the others to the other. So this is going to be 16x squared plus 120x minus 9y squared equals negative 144. And so now I have to factor out a 16, which is not so easy to do. So 16 times what equals 120. 120 over 16, 60 over 8, 30 over 4, 15 over 2. So there's definitely more algebra to do this way. Did we do this correctly? 8 times 15 is 120, so that is correct. Okay, half of 15 halves is 15 fourths. So I need to add in like 225 over 16 um, here. So when doing that, of course, what I have really done to the left-hand side is add 225. So I add 225 to the right. Okay, and this gives me 16x plus 15 fourths squared minus 9y squared equals, and whatever that is, 56 and 25 is 81. Did I do that correctly? I did. Oh. Okay, and these numbers should start looking kind of familiar if you now divide both sides by 81, then you're going to get x plus 15 fourths squared over 81 sixteenths minus y squared over 9 equals 1. And if you rewind this video, this is exactly what we got earlier. Okay, so do you see what I mean by this method being totally mindless, completely algebraic? There's lots of like annoying stuff to do, and I don't feel like I really learned anything, but arguably this is a more efficient way of converting from polar to rectangular, just doing the algebra. Okay, last method. This is the best method of all, and it's crazy that we saved this all the way to the end. Method number 4 says, yo, it's a polar curve after all. So let's just use what we know about polar coordinates. In other words, let's take your the pole, and we got some circles, 3, 4, 5, 6. Could this be better? Could be a lot better. 1 second. 5, 6, 7. And now we take our equation. The equation is r equals 12 over 3 minus 5 cosine theta. And we just take our polar coordinates seriously. By that I mean we just think of what we have as just an equation. And this equation takes as input a theta value and outputs an r value. So let's make a little chart. Here's theta and here's r. And then let's just plug in some thetas and just plot some points. All right, well, if you plug in theta equals 0, for example, then what happens? Well, just plug in 0 for cosine. Cosine of 0 we know is 1. And so this becomes 3 minus 5, which is -2. And so you get 12 over -2, which is -6. Okay, what does that mean? That means that when theta equals 0, r equals -6. Whoa. That means that I can just plot that point. All right, let's keep going. What if you give me another nice number like pi over 2? Well, if you plug in pi over 2, cosine pi over 2 is 0. And so you get 12 over 3, which is 4. All right, so when theta is pi over 2, r is 4. So boom. Sorry about that. So boom. That point has polar coordinates 4 comma pi over 2. This point has polar coordinates -6 comma 0. Okay, what else? Let's plug in pi. What's cosine of pi? -1. So now you get 3 plus 5, which is 8. 12 over 8 is 3 halves. Okay, so when theta is pi, r will be 3 halves. And so we get a little boom. This point has polar coordinates 3 halves comma pi. And finally, 3 pi over 2. Cosine 3 pi over 2 is 0, so we again get 4. Boom. Well, since I already know that this is a hyperbola, I'm just done. What does this hyperbola look like? It just looks like this. In other words, Um, with the focus at the pole, uh, and the directrix 12 fifths away, so 2.4 or whatever, by merely plugging in four quick numbers for theta, calculating the R value using the formula, and plotting the points, I just sort of instantly get my hyperbola. And in fact, where are the plugging in 0 and pi gives me the two vertices, and plugging in yeah, what was I going to say? This gives me what can I sort of glean from all this? Well, what I can glean from all this is where the center is, because where's the center? Well, it's going to be halfway between the vertices. And so here, what's halfway between 6 and 1.5? Um, it's like 9 halves, and so that's going to be 9 fourths. And so it's sort of 9 fourths away and 9 fourths away. That's 9 fourths, and that's also 9 fourths. In other words, I can immediately tell you that A is 9 fourths. Probably the smoother way of explaining that would be to say that 2A is 9 halves. Yeah, that's probably a little bit better explanation. 2A is 9 halves because it's just a fact that those two vertices are 9 halves away from each other. And so like without doing any really geometry or algebra or anything, I get that A is 9 fourths. And of course, what's C? That's even easier to find because I now know where this center is. Where is this center? Well, it's 9 fourths, away from this. So okay, whatever. Let's stop there. Um, and there's probably like another thing I can get sort of instantly. One sort of more quick thing to mention is that this segment here is actually just the latus rectum of the hyperbola. And so this distance here, which is 4, automatically tells me that b squared over a is 4. And since a is 9 fourths, then b squared is just going to be 4 times 9 fourths. So that's how I get that b is 3. Sort of very, very quickly, I can determine that b is 3 because I know that half the lattice rectum has length 4. Okay, good. These are the 4 ways of understanding, analyzing, graphing, and converting to rectangular a formula given to you in polar coordinates. First way, sort of exploiting all the different various relationships to calculate sort of a directly. The second way was by knowing that the vertex itself must satisfy the definition of hyperbola. And so using the eccentricity, we can figure out where that vertex must be. And once you know where that vertex is relative to the focus, then you know what C minus A is, and you can calculate C and A directly. Method 3, mindlessly convert with a lot of algebra the equation to rectangular using the polar conversion formulas. And method 4, just plotting the polar points and using what you know about hyperbolas to just make a sketch and just look at your own picture and just figure everything out. Okay, that's everything you could possibly want to know about this. I think this video is like an hour, so that's terrible. I'm going to turn this off now and say goodbye.